we'll just sort out microphones and she will be here.
Okay. How's that? Okay, thanks everyone. So today I'm going to focus on a few of the structures to the south and where Derek's just been talking, so he's given a good introduction, specifically on the Pilgrim, Cloncurry, and briefly on the Quamby faults. But it's that set of steep, brittle, ductile structures that stand out when you look at a map of Mount Isa. So I'll go through the geometry and evolution, and mainly using the seismic, and talk about the relationships to some of the deeper seated structures. Acknowledgements. So I've been chatting about the Eastern Fold Belt geology with a lot of people at GSQ, including Derek as well, but also working with Janelle and Dom on a seismic project. So the domains are in yellow here on the map. Now I just need to get the mouse going. Where is that?
To the right.
To the
display screen is to the right of the bucket.
Sorry, no, but you can't see my, oh, there.
Yeah, it's extended.
Okay, but then I can't see it. Okay. I was looking for the pointer, which I never use because I always arm wave. Okay, we'll get there because I'll need to point to a bit, but I can't move. Okay, so the domains are in yellow, and a lot of those domain boundaries are related to those steep late faults and or changes in geology. But the changes in geology that we see are mostly in that the cover sequences, the units that are younger than about 1800, with the exception of the Calcanoon-Leichhardt belt. So a few other faults on there that I'm going to that I'll mention. So obviously the Pilgrim, Cloncurry, and Quamby faults, the overhang shear, if I can get in here and sort of see it, and the highway thrust on the edge of the Tommy Creek block, Wollonga thrust here, just a short segment, and the Gidja shear, Gidja suture, or which corresponds roughly with the Mount Margaret fault here in this area and projects to the south. Hopefully I'm pointing at the right spot. So in general, the faults that I'm showing here in black, and I'm just highlighting a few of them, are the steeper faults. The ones that I've got colored red have generally have a more moderate dip, but we'll look at those in seismic. Now I've thrown this image in because this is from my talk from last year, and I was just saying to Paul Dirks when he came in, that in part his question last year inspired this talk, because Janelle and I were both presenting on this M6 seismic line, and she was looking at the CF3 line, which is the southern one in here. And you see a lot, just in red at the bottom, I just highlighted some of the main features I could see, some of the reflective packages, which are moderately dipping. And I'd flagged at surface where the Pilgrim Fault and Cloncurry Fault were marked at surface on the GSQ and or solid geology interp maps. And Paul, said, so, with the seismic questioned, steep versus moderately dipping structures, because it's hard we don't image steep structures in the seismic data. That's very difficult. And the fact that we see a lot of dipping structures in the seismic on more moderately dipping structures, whereas in outcrop we see a lot of steep structures. And so that is something we need to be aware of. And I just zoomed in on this example. So here we can see there's some really well-developed, moderately dipping structures. So those are, and all these seismic images I'm showing through the talk here are true dips. So vertical is roughly equal to horizontal. So that's real geology. We can't argue that. But there are other areas where we don't have well-developed reflectors, where we may in fact have steeply dipping bedding and or folded bedding that we're not properly imaging. And it will be hard to image some of those steep and especially brittle faults, but that's that's the focus of what I want to talk about today. And Steve actually drew this example for me the other day from some seismic he was looking at in the West. So if you've got a set of steep folds in seismic and you're really only getting a reflection off the more gently dipping section, then your actual seismic response may look something like this. So some of those zones, and especially near surface where we're not seeing good reflectors, this may be, in fact, this discrepancy between what we're seeing steeply folded features versus, versus not enough resolution in that shallow section to see it. So starting with the Pilgrim Fault and going back, and when I was quizzing in with Noel about this, he went back and checked, because I got to the point of deciding there's two faults that are both called the Pilgrim Fault, but they're two distinct structures. And so that's what I want to highlight here today. So the original mapping by Carter and Opic and colleagues back in the 60s defined it here in this segment on the edge of the Burke River structural zone, which is a Georgina Basin depot center. The Cambrian unit steepened towards the fault. There's some Mesozoic reactivation, and that was the original mapping. And then further north, the name was extended along the side of the Mid-Akuti area through later mapping in the 90s and early 2000s. In that zone, the dip is steep to the west, and at Kalman, just to the west of the zone, we see that's the drilling and information from the mine area says that extends down to almost 1 kilometer below surface. We have the change in geology across the Pilgrim Fault down here. And I guess at the time, this is probably just the last 10 years that the geochron has highlighted that the Bolonga felsic volcanics are distinctly younger than the Argilla. So we do have an interesting change in geology across the Pilgrim Fault. And that sort of added to the weight to the suggestion that it may be a terrain boundary. And with the seismic, until the 2006 seismic campaign, the only seismic line was the old 94 line through here, which, you know, the imaging wasn't very clear, although the reprocessing certainly helps. So in the seismic line, it's interpreted as a listric east dipping structure. So these images are from the Korsch publication workshop at the end of the PMD CRC. You can see the extent, the Burke River structural zone. So it's not necessarily a structural zone. It's just sort of how it appears in plan view, but in cross section, we can see it really is a half graben with controlling structures here on the left-hand side. Now, the location of the Pilgrim Fault that I've highlighted here is the one that was used in this interpretation. And the westernmost Cambrian units sit in here. The interpretation at that time, there we go, dominantly listric east dipping structures. And we can certainly see those. I'll flick, when I go through most of these images, I'll flick back and forth a couple of times. So we can see, this is the same image I was showing earlier, this really well-developed 20 to 30 degree east dipping package of reflectors. And we still see the east dips through here. They're a bit more discontinuous and a bit broken up. We still get some east dips over here, although we clearly see some breaks in those packages of east dipping reflectors. So that was the interpretation there. But when I went and looked more specifically to think about brittle versus ductile structures, so this image just highlights, this grayscale mag, you can see the change, which I can't really see what I'm pointing at because it's too far over. So you can see this prominent magnetic anomaly and the fault in red drawn along that. So that is an east dipping fault, and you see it very clearly in the CF3 line to the south. And that correlation was made with the Pilgrim Fault at the time the seismic interpretation was done. So I don't know enough about the sequence events, but by the time they were interpreting this, because they were interpreting it as a major structure, the Pilgrim Fault, and it's still located in the digital geology maps along the edge of this magnetic anomaly. Whereas from outcrop, we would call it a steep west dipping structure over here. So we've ended up with two separate Pilgrim faults. So then I'll show you the interpretation, the working interpretation I've got. And highlight across the top here. So I've just got a couple of tick marks. So this first one shows the edge of the Cambrian units. This next one shows the edge of shallow basement. So we've got Leichhardt volcanics to the west, and you can see them quite clear in the mag. They get a bit deeper, but across this structure, you really lose the response of those Leichhardt volcanics. It is fairly subtle, but a subtle response, but you lose it across that structure. This is where you see that big magnetic change that I was just highlighting. We can see the stratigraphy of the Georgina Basin is really well developed. It comes right across the top of that feature. And then we've got a disturbed zone at the western boundary of that basin, of that graben. So there's my fault interpretation. I've linked the steep boundary and the main change in where I'm losing the Leichhardt volcanic response to this broken zone of reflectors at sort of 3, 4, 5 seconds two-way time. Now, I'm not going to say this is the interpretation, but based on, you know, bringing all the data together, this would be my preferred interpretation. This structure extends down to at least about 6 seconds. There is a structure, and we'll see this one on the next seismic line to the south, that is gently dipping below it. It's certainly disrupted. Whether it truly cuts it or how much offset there is unclear. So the east dipping structure that's probably responsible for the change in the main change in magnetic response is truncated by another steep splay. It does not show up in this seismic line. You know, I've dashed it in there because, you know, based on the mag, I know it's going to be there. But I'll show you another seismic line where it is really obvious. So that's just the mag image to show we're jumping down here now to this line, and you can see these two features are much further apart, and it's really obvious. So again, this is the limit of shallow basement. We've got a little bit more cover here, so it's not a really sharp change in that magnetic anomaly. That's the really obvious change in the magnetic data. And you can see we've got a really well-developed sort of 30-degree, 40-degree dipping shear zone there in the basement. I'll just flick back and forth a couple of times so you can see that structure. The western boundary of the graben again relates to changes, breaks in the reflectors here. We've got a steep west dipping package of reflectors that ends in this zone. And so you can easily correlate a steep west dipping structure that you can see, have evidence for in the seismic, and you can correlate that through to the edge of your basin. Now I will zoom in just to show you that a bit more clearly. So the base of the Georgina, there's a fairly bright reflector through here. That's easy to pick. We lose it a bit over here. You can see we've still got a really nice developed package of reflectors in that young basin with a fairly steep, we've got a bit of disruption, but certainly a fairly steep western boundary. So again, there's the faults in green, the approximate base of the Georgina. So then these two faults that have both been named Pilgrim Fault, I had a chat with Ian, with Noel and Janelle and Dom, and sort of said, okay, if we're going to have to change or propose a new name for one of those, which one is it going to be? And I think fundamentally, it's always going to be harder to change what's there in outcrop, and everybody's been looking at and thinking about on maps for a long time. So I've made the suggestion that the Pilgrim Fault, the name remained for the western boundary of the Georgina Basin Depot Center, the Brook River Zone, and that is a steep west dipping structure, and that links through with what we see in outcrop. Whereas this east dipping structure, I proposed the name Black Mountain Fault. The Black Mountain drill hole is just along that structure. Now that east dipping structure is probably equivalent to the Bolonga thrust. which is mapped in outcrop and interpreted in the seismic up on the old 94 line, and that was the work by Marco Day. Cloncurry Fault Zone. Most of the outcrop summary I'm giving you is from Austin and Blenkinsop. So there's about a 100-kilometer segment there that outcrops. It's about 7 kilometers wide, subvertical, east dipping. The main fabrics in there, post-date peak metamorphism, which is about 650 in this area. There are mylonites, and they mapped and sampled and analyzed the mylonites that formed at about 350 to 500 degrees C. And those mylonites also overprint the Marramungi granites, confirming that age relationship and making it post-D2. So the shear zones anastomosing and the geometry of the shear zone is consistent with the D3 east-northeast shortening. Whereas the brittle overprinting structures then are more consistent with the D4 east-southeast shortening. They're associated with sodium-calcium alteration and brecciation, and they interpret it as a crustal scale structure. It's also been flagged as initiating as a normal fault, and I initially agreed with that and have stated that probably last year here and in other talks. And it's again interpreted as a listric east dipping structure in the M6 seismic lines on both M6 and M5. So we'll have a quick look at both of those. So again, this is the interpretation from Russell Korsch and the team with the surface position of Cloncurry Fault flagged there and Cannington roughly projected. So you can see there's a change in dip across the fault zone, if I can find my mouse, from east dipping to west dipping, and that's reasonably well defined when you zoom in and look through there and down to here. This image only goes to 6 seconds, but they do have it listric at depth. So you can see that change in dip, and my interpretation is very similar there. But the thing that I've brought in, I've just got an image that's the colors gravity and the textures mag, just along that belt. But we have to also think about the granites in this area. So I've used the Deep Mining Queensland 3D granite model and used that to guide my interpretation of where the granites are on this line, but I've modified it to be consistent with the magnetics. So whereas the DMQ model, this main body was more shallow, and I said, okay, I've got a really nice fabric here that's not part of a Williams Suite granite. So my granite has to be a bit deeper here. It has to be between this good package of reflectors and this good package of reflectors. And this area in here is a bit more, is more modified. So we can see the Cloncurry Fault is very similar position here, and it's reasonably well defined with the breaks in these east dipping or west dipping reflectors. Now I'm going to go to the next slides, and I'm going to talk about this offset in the Gidja shear zone. So this is basically the moderately dipping, gently dipping boundary between the Numel crust to the east and the Mount Isa crust to the west. We can see that boundary's folded quite clearly based on the reflectors here, and it is cut by the Cloncurry Fault. So you don't see on this image, you can't clearly see how much that offset is or if it's definitely in that normal sense, but on other lines you can see that more clearly. Oh, yes, I've said that. So this just zooms out, and I put some quick color on it to help you see things. So the Numel in green, and the location of the suture here is constrained by where it sits here. So and I know you can't see it clearly on this image because I'm too zoomed out, but we've got some pretty good reflectors here that control where that suture zone is coming up. And we know it has to be folded. And then the link with the M5 seismic line says it has to be reasonably deep or an off here. It can't come up too high here. And just the Pilgrim Fault on that side to get your scale. So I'm going to step quickly to M5, and then we'll go back and look at another line. So this is from that same workshop session. Ian Withnall was presenting the results for the lines over in this area. So there's Cloncurry Fault here coming down, Listric into a zone here. And my interpretation is very similar to this. I just don't see the Cloncurry Fault as being Listric into that detachment zone. So I've got it remaining a bit steeper here with an offset in that Gidgee suture. There are a couple of strong structures here to the east of the Cloncurry Fault that could be the Gidgee suture or a splay. And I originally was thinking it might be this feature in here, but I think it's got to sit a bit further west based on looking at, sorry, a bit further east, based on looking at all the seismic lines. So just a quick comparison. You can see that's very similar. I just see more continuity through these reflectors here and didn't want to try and have the structure come right through. Now, we've jumped south again, so we're looking at the CF3 line, which really highlights some features. Now, I know this is really busy, and I will zoom in, but I just wanted to zoom out and show a couple of key things, because here you can see a really nice package of reflectors. So we know where that suture zone is. We've got the really strong reflectors in the numal crust coming through here, and you can see these east dipping reflectors in the lower part of the Black Mountain Fault we were just discussing that come down and do not cut that Gidgee suture. So we've got really good control on its position here, and we've got really good control. So, you know, this is just, you know, like when you're looking at magnetic data and you're looking for truncations between your magnetic anomalies, this is just the same thing we're seeing here. We've got west dipping reflectors here in the numal crust and this strongly east dipping package of reflectors here. So we know exactly where that structure is here, and that's where I have more confidence in that normal sense offset in that zone across the Cloncurry Fault. So just zooming in so you can see the Cloncurry Fault in a bit more detail through there. It's not really well defined in this upper section. So we do have granites coming in through here, but this might, you know, in this upper section where we're not seeing good packages of reflectors, this may be one of those areas where we've got a bit more folding and some steeper folding that we're just not imaging well in the seismic. And as we get a bit deeper, those packages of rock are not as tightly folded, and we see them there. So we've got some breaks and some offsets coming down through here. This section's probably a little bit less clear, and then we're a bit better down here. So Quamby Fault, I'm just going to talk about very briefly, because I think there's one of the seismic lines that crosscuts 3 lines up here, but the M4 line constrains the dip direction of it. So surface position of the Quamby Fault, the Roseby, I don't think shows up very well, but the Quamby here, as a steep fault, you can see this really nice packages of reflectors below about 2 seconds down to 5-6 seconds 2A time. It's pretty hard to put a steep west fault through that package of reflectors. So instead, you're constrained for the Quamby Fault zone to be steep east dipping down through here, because we've got this nice package, but we do see it broken in this area. Roseby doesn't show up very well. There are some breaks in reflectors here. The highway thrust is the only other one I'll highlight. So you're fairly oblique up the edge of the top edge of the Tommy Creek block, but based on the packages of reflections here, it looks like a moderately west dipping structure. Really focused the Pilgrim Fault. I think we need to keep the name Pilgrim Fault to the steep west dipping structure. We see that clearly down to 4 or 5 seconds, and it does control the depot center in the Georgina Basin. It itself is not east dipping, Listric east dipping, but it's in the same zone around other east dipping structures. Cloncurry Fault, steep west dipping, and goes down and offsets the zone between the Mount Isa and numal crust. I haven't really talked about the granites in detail, but you can see that relationship. So that, as Derek was talking about, and sorry, I wasn't paying attention to the time. I always think I'm going to talk fast and then I slow down. So we have a lot of early low-angle structures that formed during extension when you deposited the Soldier's Cap group, Currydala group. So during D1 and thin skin shortening and the main D2 east-west shortening and crustal thickening, you reactivate those. They reactivate readily, and the pneumal is under thrust beneath the thick Mount Isa cross to the west. But by the time you get to D3, D4, and those shortening is more oblique, those structures are not optimally oriented to reactivate. So they start to lock up, and after D2, well, lock up and fold. And then it's during that, as we go to oblique shortening during D3 and D4, that we get structures like the Cloncurry Fault and Pilgrim Fault forming. So other steep structures may have an early history. I think from what I'm seeing here on these ones, I suggest both of these are dominantly late. So where we see them here in the seismic, we'd say they're dominantly in the upper crust. They do link through to the deep-seated structures, some of which are blind in terms of linking into those first-order fluid conduits. But I wouldn't say with a lot of confidence that they're not lithospheric scale themselves. They may be. We certainly see some breaks, and maybe we're just not seeing them clearly in the deeper crust. But the segment we really see that's well developed is in the upper crust. And sorry for not paying closer attention to the time. Thanks.
Thank you so much, Karen. Any questions for Karen? Oh, lots. For those online, JCU are working on similar interpretations and their hands shot up very fast. Johan.
Thanks, Karen. My question is, in the field, and actually probably even if you look clearly in magnetics, you can see that Pilgrim Fault as well as Cloncurry Fault are quite wide deformation zones, and they're quite steep, and the fabric, it's quite high-grade fabric. But locally, you see this late overprinting, which is clearly a fault zone. So I was thinking of this structure more like shear zones. They've been overprinting by late fault structure. So do you think that it's possible what you're actually seeing in seismic is the late fault overprinting on an earlier shear systems?
I think yes, and I haven't seen the exact spot, and it'd be good to look together in plan view at the maps, because I think these structures are forming within a highly deformed zone, a highly deformed belt in general. And I suspect in one area they're overprinting one structure, in another area they're overprinting another ductile structure. So if you think of it cutting the Black Mountain Fault in the south, you would, where it links in and is cut, there would be ductile features related to that structure, and the same with the Bolonga thrust and other structures. So that's my working model now. I haven't seen the rocks in the field that you've seen. So I wouldn't rule out the option that there is so you see it as a ductile steep structures.
Ductile deformation zones.
So, okay.
They can be quite
peak metamorphic or post-peak metamorphic?
Well, I think some of them are definitely peak metamorphic.
Okay.
Sorry, some of them are peak metamorphic.
Okay.
Yeah,
well, yeah, it'd be nice to sit down and chat about that.
I've got another one along the same lines. The metamorphic pressures we see on surface vary from 3 to 6 kilobars or so within the Mount Isa block. So the upper crust, all structures you show, they're down to 5, 6, 7, 8 seconds, should be a reflection of the geology we see on surface, sort of. Yet the geology we see on surface doesn't look anything like the pattern of reflectors you show on the top 5 seconds in some of these sections. And it makes me wonder what these reflections really are. Now, the one thing we do see is gradual thermal gradients, and we see a lot of regional alteration. And some of that alteration has the capacity to completely and utterly change the composition of rocks over very large areas. So my question is it possible that some of these gentle reflectors you see moving through the landscape that really don't reflect structure could reflect alteration fronts of some sort?
I think there's a range of sources. I think some of it is clearly primary bedding layering. I think in some areas, and because I've spent a bit of time looking at the Soldiers Cap group, Curried Island group, I think, you know, we certainly see some zones where those reflections are much stronger, and those are probably the mafic sills. You can see swarms of the mafic sills and through there. And there's certainly alteration, and then there's certainly overprinting structures, which won't be at the same orientation as the original bedding. But looking at the seismic, I feel like a lot of that is, you know, primary or broadly primary. Like there may be recumbent folds in there we can't see, you know, but that broad layering, it'd be pretty hard to argue that it's not, based on my experience, but you know, it'd be good to sit down and look at zones together, you know, where we are close to the seismic line, and think a bit harder about that. And are those zones where we see some good reflections or not? But on the east zones of those lawns where we see those really nice east dipping packages of reflectors, ooh, I think those are real. And that it's got to essentially be, you know, deformed bedding.
I might ask